In this video, we're going to be looking at calorimetry, the measure of heat changes or heat transfers. The two quantities we're going to be calculating most often are specific heat, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, and heat capacity, the amount of heat required to raise the temperature of an object by 1 degree Celsius. The specific heat of liquid water is 4.184 joules per gram Celsius. In heat capacity, we have to specify the mass. So the heat capacity of 1 gram of water is 4.184 joules per degree Celsius. Notice the difference in the units. This will be important as you do these calculations. We're going to be looking at the amount of thermal energy transferred given by Q. If we think about the amount of thermal energy transferred, if a reaction is giving off an amount of thermal heat, the surroundings are going to have to absorb that heat. So therefore we can come up with a simple formula where Q is equal to the Q of the reaction plus the Q of the calorimetry. This is going to have to equal 0. So therefore Q of the reaction is equal to negative Q of the calorimeter. The other formulas that we're going to need for thermal energy transfer, one is based on heat capacity, the other is based on specific heat. For heat capacity, the thermal energy transferred is equal to the heat capacity times the change in temperature, or symbolically, Q equals C delta T. For specific heat, the thermal energy transferred is equal to the mass times the specific heat times the change in temperature. Symbolically, Q equals MS delta T. The other thing we need to be aware of when we look at calorimetry problems is there's actually two basic calorimetry type problems. One with constant pressure. Constant pressure calorimetry is very common and can be done with a simple coffee cup type calorimeter. Constant volume calorimetry requires a specific type of calorimeter, a bomb. Therefore, it's often called bomb calorimetry. First, we're going to look at an example problem looking at using constant pressure calorimetry. Then we'll look at a constant volume calorimetry problem. The problem, 9.0 grams of aluminum at 100 degrees Celsius are placed in 20 milliliters of water at 20 degrees Celsius, contained in a coffee cup calorimeter. At thermal equilibrium, the temperature of the water and the aluminum is 27.1 degrees Celsius. What is the specific heat of aluminum? Okay, again, remember that the thermal heat transferred, Q, will be equal to 0. And here we have the heat transferred, Q for aluminum, transferred into the calorimeter, Q cal. So therefore, Q for the aluminum is equal to negative Q for the calorimeter. Since we've been given the specific heats for these, or we're actually looking for the specific heat, we can use the specific heat formulas. So Q equals MS delta T. If we substitute those in, we'll see that we have M aluminum, specific heat aluminum, change in temperature for aluminum is equal to the negative of the mass of water times the specific heat of water times the change in temperature of water. If we do a little algebra, we get specific heat of aluminum by itself is equal to negative mass of water times the specific heat of water times the change in temperature of water over the mass of aluminum times the change in temperature for aluminum. If we look at the values we need and the problem, we can come up with some of these very quickly. Mass of aluminum is going to be 9.0 grams. Mass of water is going to be 20.0 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. For temperature, we know that the change in temperature is equal to the temperature final minus the temperature initial. Therefore, the delta T for aluminum will be 27.1 minus 100 degrees Celsius, which is negative 72.9 degrees Celsius. For the change in temperature of water, we have the final temperature, 27.1, minus the initial temperature, 20.0, which gives us 7.1 degrees Celsius. Plugging this all in, we get the specific heat of aluminum is equal to negative 20.0 grams multiplied by 4.184 joules per gram per Celsius times 7.1 degrees Celsius, divided by 9.0 grams times negative 72.9 degrees Celsius. We can see that on the top of our formula, the grams cancel out and the Celsius cancels out, leaving us just joules. When we do our calculation, we see that the specific heat of aluminum is equal to 0.90 joules per gram degrees Celsius. For the constant volume calorimetry problem, we're going to look at a combustion problem. This is very common for constant volume type calorimetry or bomb calorimetry problems. Problem: combustion of 1.00 grams of sucrose causes the temperature of a bomb calorimeter with a heat capacity of 4.90 kilojoules per degree Celsius to rise from 25 degrees Celsius to 28.41 degrees Celsius. What is the heat of combustion of 1.00 grams of sucrose? In this problem, we see that we have a bomb calorimeter and they're giving us the heat capacity of the bomb calorimeter. Therefore, we're going to use the Q equals heat capacity times change in temperature, or Q equals C delta T. Again, we know that the heat given off by the combustion is being absorbed by the calorimeter, so Q of the reaction equals negative Q of the calorimeter. Therefore, we can plug in our values and get Q reaction is equal to negative heat capacity of the calorimeter times the change in temperature for the calorimeter. The heat capacity of the calorimeter is given in the problem, 4.90 kilojoules per degree Celsius. The change in temperature is going to be 28.41 degrees Celsius minus 25.00 degrees Celsius, or 3.41 degrees Celsius. Plugging those in, we see that the heat of combustion is going to be negative 4.90 kilojoules per degree Celsius times 3.41 degrees Celsius. Doing the mathematics, we get negative 16.7 kilojoules. Again, these are both simple problems, but if you just follow your units and you look at your equations, you should be able to look at the other derivative type problems you'll see for calorimetry.